This is a video for how to go about creating both a polar graph and a linear graph from the cam rotation and follower placement of your Automata box. Now, for our Automata box, we have 4 to 5 different cams. You'll see an eccentric cam rotating here. You're going to see a hexagon cam, kind of gives that consistent vertical motion of the red follower. The snail cam is more of kind of a drastic drop off after it rises that you see in the snail cam. And then the pear cam kind of is something, it almost looks like a squirrel peeking its head up out of the ground with the way that follower goes. Now we also have a heart cam within the Automata boxes that we choose, but you're only going to see the eccentric, hexagon, snail, and pear cam here. So notice that as the cam is rotating, it is rotating 360 degrees, and its angle of rotation directly correlates to how high the red follower is moving along the ruler that we see here. So we could say, at 90 degrees, the red follower is here. At 45 degrees, it's at a different angle. At 0, it's at a different angle. At 285 degrees, where is the follower going to be at? And we can actually design the cams to give a consistent and expected output of that red follower. Now, within the spreadsheet that we're going to be looking at, you'll notice that there's 2 separate cams within an Automata box. So in the Automata boxes in my classroom, we have 2 separate cams. And what we're saying, at 0, the height of the follower on the left side is at, 1 1/4 inches, and on the right cam, it's at 2 1/8 inches. And if we can look at an example here, you can see that there's 2 different types of cams. There's a pear cam and there's an eccentric cam. And as both of them rotate with this specific Automata box, those blue followers are at different heights. They rise and fall at different heights. And what we're saying is the left cam at 0 degrees is at a certain height, and that right cam at 0 degrees is different. You can see that green cam right there is pretty much staying right at the same spot until it gets one certain type of rotation. Because it only rises, because it's a pear cam, it only rises at a very specific degree of rotation. That eccentric cam is a constant movement of vertical following of this blue follower. So you can see it really only rests for a split second, and then it's always moving. The green cam, that pear cam, really kind of rests at a spot and only rises up at a specific time. So if we wanted to make a graph to chart that information, we can place all of our inch numbers in here, and we can go in and create charts and graphs. So what we're going to do to create this chart is we're going to highlight all of our data, including the titles up at the top, and we're going to go to Insert, and we're going to go to Chart. And once we go into Chart, you can see right here it automatically goes to a line chart, but I'm in a polar chart. So I'm going to click on Line Chart, and I'm going to come all the way down to here to a polar chart. This is what we want. And a polar chart is kind of looking at a center point, if you will, like a center point of the object. And what we can see is the rotational degrees are around the outside of the circle. So I can say for my left cam here, I could call it whatever name of a cam I wanted, at 180 degrees, it's about at 2.125 out here. I can see that at that specific number. I actually look at my chart and say there's 180, 2.375. I was a little off. It's a little further out. I can look at, the red cam right here. It says right cam. I can say, at 0 degrees, where is it at? And that right cam at 0 degrees, I can see it's right at about 2.125. I should be able to look at a chart like this and actually know exactly where that follower will be based upon reading a chart. So I got my chart made here, and I'm going to kind of decrease the size of it. I'm going to drag it over here to the side. That's the polar graph. I have another tab down here at the bottom for a linear graph. We're going to do the same concept. We're going to highlight everything. We're going to go to Insert. We're going to go to Chart. And it's going to default to a radar chart. We want this a linear graph right here. And for this linear graph, you can see that it's automatically charting everything. So I can see the angle of rotation in degrees. So at 100 degrees, I can see that my left cam should be just, 1.75-ish. I can kind of take a look. We can do more minor grid lines. We see some major grid lines in here. I won't make you do that, but we can go in and actually see what height everything should be at 0. So at 0, I'm at 1.25. Now watch what happens if I say, at 0, it's actually at 0.75. Let's see what happens. And it's automatically going to adjust and move off. I need to put in 0.75, sorry. So if I go to 0.75, my graph will automatically change. Now if it's back to 360 and 0 are the same. If I put in 0.75, it'll automatically adjust and show what the chart will be. So when we actually start physically making boxes, we can go back and we can just change the data as we read and we rotate, and our graph will automatically adjust. Pretty cool thing that you can do within chart creation in Google Sheets. So in creating charts, it allows us to look at specific information from an exact box and read where the followers will be in relation to the rotation of the cams. The whole entire point of an automata box is telling a story of what happens when a crankshaft is rotating and how those cams behave. You're trying to get the blue followers that you see here to go up and down. And we're trying to be able to read a chart and say, based upon where we want the follower to be, we can change the cam to tell the follower what to do. It's rotational motion to vertical linear motion. That's what we're learning in class. And everything that we see is designed through geometry. You went in and designed each one of those cams. Each one of these cams that you see here, we use parametric equations within Fusion to design these, and then we can go back and change the numbers in those parameters, and our automata box will automatically adjust. And we can go back to our spreadsheet and change the numbers. So remember, everything that you look at that's designed by somebody or designed by an engineer is, the definition of engineering is the use of math and science to solve problems in society. And we're using math and geometry and materials to solve a problem of taking cams and having rotary motion and having them convert to linear motion that we see right here. So this has been a video for how to go about creating a polar graph and a linear graph from data collected from an automata box in your Introduction to Engineering Design class.